Hello everyone, in this video we will talk about the specific energy and its application in open channel flow. So first of all, let's start with the energy and momentum correction factors. So as we know, whenever we are solving any equation, we take the average velocity, and so we bring some error in this, and if the variation is more in the channel, like this is the cross section, and we know that velocity cannot be same at every point because there will be friction near the boundaries, so velocity will be less near the boundaries and more near the center portion. So it is not same everywhere, but if we are putting using average velocity in our equation, then we are introducing some error. So to counter these errors, there are some correction factors. So two of these correction factors we are talking here. First is alpha, that is kinetic energy correction factor, and beta, which is for momentum correction factor. So let's find out. So we know that kinetic energy is given as half mv square. Now if first of all, alpha, which is kinetic energy correction factor, it is defined as kinetic energy based on the actual velocity divided by kinetic energy based on the average velocity. So to find out the kinetic energy based upon the actual velocity, let us consider a small elemental area, and it is having an area of dA, and a velocity of flow through this area is small v. So I want to find out the mass per unit time through this area. So flow through this elemental area will be v into dA, and if I want to find out the mass, so it will be rho q, which is rho v dA, where rho is the density of the fluid. So this is the, and for the elemental area, what will the kinetic energy? It will be half, this is the mass per second, is rho v dA, and so it represents the mass and v square. So I can write it as half rho v cube dA. And so here kinetic energy based on actual velocity, if I want to find out, this is for the elemental area dA, and if I take such many elemental areas which are there in this complete channel, so it will be integration of half rho v cube dA. So the alpha is equal to integration half rho v cube dA, and kinetic energy based on the average velocity will be let's say average velocity through this section is capital V, and so it will be half V A, this will rho half V A, this will represent the mass into V square. And if we are talking about the water, then the density of fluid will be constant, so we can write it as V cube A divided by V cube dA divided by V cube A. This is alpha. And similarly, beta is defined as momentum based upon actual velocity divided by momentum based upon average velocity. So momentum is given as m into v, and similarly mass we found out from here, it was rho v dA. So we can write beta as integration of rho v dA into v. This is the momentum based on the actual velocity, and momentum based on average velocity will be rho v a into v. So beta can be written as integration v square dA divided by v square a. This is it. And so both of these factors are greater than 1, and alpha is greater than beta normally, and which both of these are greater than 1. Now the specific energy. Specific energy we defined earlier also. This is the, we define it as the sum of flow depth plus velocity head, but this is nothing but the total energy. Total energy taking channel bed as datum. So if I consider this channel bed as datum, and from here if I want to find out the total energy at these points, so it is the sum of pressure energy plus velocity head, and I know that this is the, we consider the hydrostatic pressure distribution. So the pressure here will be gamma y upon gamma plus v square upon 2g. So this is y plus v square upon 2g, which is the specific energy what we are defining here. And so in a uniform flow we can consider it as a constant. Why is it so? Because in uniform flow, flow depth does not vary, any flow parameter does not change with the within the length of the channel. So y is remaining constant, same is for velocity. So if flow depth and velocity are not changing, so from here we can see that E is also going to be the same. So in the whole channel reach, specific energy is constant. But in any real fluid flow, the total energy will always be decreasing, because there will be a head loss in the direction of flow. So total energy line will be something like this. It will always be coming down. But if we are assuming the channel to be frictionless and no head loss, then we can say that the total energy line can remain horizontal, but with some assumption. And the hydraulic gradient line in this case, in open channel flow, it remains with it coincides with the surface of the water. So this will be the hydraulic gradient line. And so as we saw the kinetic energy correction factor, so the proper representation here should be y plus alpha v square upon 2g. But in the channel normally the flow is in turbulent condition. So when the flow is turbulent, alpha is almost equal to 1. Or if we are talking about the uniform flow, then also alpha is equal to 1. So we can approximate it as y plus v square upon 2g. Now let's see the specific energy diagram. So specific energy diagram is the diagram derived from the same formula as we saw above. So when we plot E versus Y in this equation, E equal to y plus v square upon 2g. So this line here, it is at 45 degree, and it represents the E is equal to y condition. And as we are adding something to this, so the here it is specific energy and depth, so we are adding velocity head to this. So this this curve will always be on the right side of this line because there is the addition of velocity head. So when we plot it, it comes out to be like this. Does not touch here, but it comes like this. So from here we can see that for any specific energy there are two depths of flow for the same specific energy. If I take this as the specific energy line, so from here I can see that it is corresponding to the some depth y1 here and also some depth y2 here. So at both these points the specific energy is remaining same, and so these two depth are called as alternate depth. And so why is it happening so? Because specific energy is the sum of depth plus velocity head, so com we can have two combination of these two parameters to find out a same specific energy. If we are taking smaller value of y and larger value of velocity head, then also we can have the same value of velocity, same value of specific energy as the case when we have larger value of y and smaller value of velocity head. We can see it from the graph also. If this is the velocity head, then the remaining height from here to here, it will represent the, if this is the flow depth, so this will represent the velocity head, and in the other case if from here to here it is the flow depth, then this smaller height, this will represent the velocity head. So we can have two values of depth for one specific energy. So this is the case everywhere except for this one point. At the minimum specific energy level, when E is E is minimum, at this point y, there is just one value of y, which is known as critical depth. So at this depth the specific energy is minimum. From what is the significance of this depth? Apart from this depth there are always two depth of flow for the same specific energy, and from here we can say that this is dividing our area into two parts. This top part will represent the subcritical flows region, whereas this bottom part will represent the supercritical flow region. First we'll try to find out the critical depth from this equation. So here we saw E is equal to y plus v square upon 2g, and we can rewrite it as y plus q square upon 2g a square. And if I take q as a constant for same value of discharge, if I want to find out the minimum of specific energy, so for that dE by dy should be equal to 0, because depth is the only parameter which is changing. So from here if I differentiate this equation, dE by dy is equal to 1 plus q square by 2g is constant, d upon dy into 1 upon a square, and this we can denote as d by dy is equal to 1 plus q square upon 2g. This will be minus 2 upon a cube into dA by dy. And now for this dA by dy, in a channel if I consider a small strip from the top, so this is the top width t, and the depth here if I take it as dy, so this area will be dA, which is equal to t into dy. and from here dA upon dy is equal to T. So we can put that here in this equation, and it will be 1 minus q square T upon GA cube. And from here we saw that for specific energy to be minimum, dE by dy should be equal to 0. And so from here we get the condition q square T upon GA cube is equal to 1. This is the condition for critical flow. We can further derive from this by rearranging the parameters. Q square upon A square into T upon G by A is still equal to 1. And from here Q by A is equal to V. So V square divided by G into A upon T is equal to 1. And this A by T is the hydraulic depth, which is the ratio of area divided by top width, and we represent it as D. So if I write it as D and take the under root, so this is equal to V upon under root GD is equal to 1, and which is the Froude number. And so Froude number is equal to 1. This is the condition for critical flow. So from here we can see that at critical depth, like for YC, F is equal to 1, and flow depth, if it is greater than YC, so F will be less than 1, and if it is less than YC, then Froude number will be greater than 1. So this is the critical flow. This will be subcritical flow. This will be supercritical flow. So using these we can classify our flow, and it will help our in solving questions. Now the next is our specific energy versus discharge. Now in the same equation, E is equal to y plus q square upon 2g a square, if instead of q I say specific energy E is constant, and from this curve I can denote it as, I am putting certain value of E here. This E is constant, and so we can say that if I increase the discharge, this curve will shift to the right, and so it will keep on going like this, and there will be a curve such that it will just touch the specific energy line. And if I increase the discharge further, there is no intercept between the energy line and this curve. So what does it imply? That with this specific energy, this flow cannot pass, and if it is only possible if I increase the specific energy to pass this flow. So this we will use when we use the application of the specific energy to find out the flow through the transitions and how the depth varies in the transition case. But here we can see that the maximum discharge which can pass through specific energy will come when this discharge flow just touches the specific energy line. So it will come at the critical depth. We can find out this using this equation also. From here I can say Q is equal to under root 2g a square E minus y. Here E is constant, so variable are a and y. So if I if I want to find out the maximum discharge for this constant specific energy, for that dq by dy should be equal to 0. So what will be the value of dq by dy? Dq by dy is equal to under root 2g, which is constant, and a upon 2 under root e minus y into minus 1 plus under root e minus y into dA upon dy, and this will be equal to 0. So from here a upon 2 is equal to e minus y, and we saw earlier also dA by dy is equal to t, and e is equal to y plus v square upon 2g. So from here e minus y is equal to v square upon 2g. So putting it here, a by 2 is equal to v square t upon 2g, and v square is the v square we can rewrite as, this will cancel out, v square we write as q square t upon g a square, and from here q square t upon g a cube is equal to 1. Which is the case for critical flow. So from here we can see that for constant discharge, for constant value of specific energy, Q is maximum at critical flow. And one more thing, for constant discharge, specific energy is minimum at critical flow condition. Next is our critical depth calculation for channels. So first let's see for rectangular channel. This is the rectangular channel, and let's say this bed width is b and the depth is y. So area is equal to b into y, and top width is equal to bed width, which is equal to b. So for critical flow, q square t, as we saw earlier, upon ga is equal to ga cube is equal to 1. If we put the value of area and top width here, q square b divided by g b cube y cube is equal to 1. If we rearrange this, so I can write it as y cube is equal to q square upon b square divided by g, and this is the unit discharge, which is discharge per unit width. So y here is equal to q square upon g to the power 1 by 3. And as we know, Froude number is equal to 1 for the critical condition, and Froude number in this case is equal to under root g y is equal to 1, because d is equal to a by t, and if I put by upon b, d is equal to y, and from here b square upon g is equal to y. And if I want to find out the specific energy at critical depth, so which is equal to y plus b square upon 2g. So y plus v square upon g is equal to y, so y plus y upon 2. So this is equal to 3 by 2 YC, also YC. Similarly, let's do for the triangular channel also. So this is the triangular channel. And if I take the slope as m is to 1, so and this depth of flow is y, so this is equal to my, and similarly this is also equal to my. So t is equal to 2my and a is equal to my square. And for critical flow, q square t upon g a cube is equal to 1, and if we put these values, q square into 2my divided by g into m cube y to the power 6 is equal to 1. And we solve this. From here we will get y to the power 5 is equal to 2q square upon gm square. And from here y is equal to 2q square upon gm square to the power 1 by 5. And as we know, Froude number is equal to 1, and in this case hydraulic depth d is equal to a by t, which is equal to a as my square, and top which is equal to 2my, so d is equal to y upon 2. If I put in the Froude number formula, which is under root g y by 2 equal to 1. From here v square upon g is equal to y upon 2. If I want to find out the specific energy at critical depth, this is equal to y plus v square upon 2g, which is equal to y plus v square upon g is equal to y by 2, so this will be equal to y by 4. So EC is equal to 5 by 4 YC. So the specific energy. Now there is one more term in this, which is called as section factor. So it is denoted as Z. It was used earlier to find out the critical depth. So nowadays it is not used because computational power is there. So it is denoted as Z, and it is defined as A under root A by T. And for critical flow condition, we know that q square t upon g a cube is equal to 1. So from here a cube upon t is equal to q square upon g, and if we put it here, so z will come out to be q upon under root g. Next is the channel transition. So channel transition we use to find out that there are some uses, such as to find out the velocity of flow or the discharge through channel, or if we want to dissipate some energy. For these purposes we use the channel transition. So in this, because this is a small length, so we are assuming some things, which is the total energy line, it is horizontal, and which implies that there is no friction loss, or say head loss. There is no head loss through the channel. So based on these assumptions, we'll try to study the channel transitions. So first is the hump. Hump is nothing but if we if we raise the bottom of the channel at some distance, it is known as hump. So for this, we study it using our specific energy diagram. So here we here our specific energy diagram comes to use. Let's say this is E and Y, and from here we can see that this is the critical depth. Here there are two cases. If this incoming flow is in subcritical zone, or the next will be if it is in supercritical zone. So first we will see for the subcritical zone. So from the specific energy diagram we can see that if, let's say, this is the specific energy at section 1, and because we are putting a hump, there will be a reduction in specific energy at section 2. We can understand it here, like total energy is remaining constant in the channel. So if this energy is E1, so here if I write the equation for total energy from this channel bed, it will be E1 is equal to, at section 1 it is E1, and for section 2 it will be delta Z, which is the height of this hump, plus E2. So here E2 is less than E1, only then these two can be equal. So from here in the specific energy diagram we can see that if this is the specific energy at section 1 and this is the energy reduction in section 2, and this will be the height of the hump. So if we are in the subcritical region, which is up from here, from the critical depth, so if I increase the height of the hump, what will happen? The depth of flow is section 1 is something y1. So if I'm putting a hump of height delta z, so depth of flow is reducing, it is coming down to y2. It can be understood in such a way that here the specific energy is large, so there is large depth, and here the specific energy is getting reduced. So for that reduction will come through the reduction in depth, and due to this reduction the velocity of flow will also increase at this section. So what else can happen here is, if I further want to increase the height of the hump, so this line will come somewhere here, and so this will be the delta z, and further this depth will reduce. So from here we can see that this depth will come down something like this, and if I further reduce it, so I'll reach this point where delta z is maximum, and at this point the downstream depth, this y2 will come here, and which will be equal to critical depth. And so if I keep on reducing it, so this y2 will reach equal to the critical depth. And what will happen if I want to increase the height of the hump further? So if I increase the height further, so it comes something like this. Let's say something here. So there is no intercept between the between this curve and this line. So there is no depth possible for this height of hump. So what will happen here? Here the specific energy at section 1 will increase. Then only this height of the hump, increased height of the hump, can be provided. So if I increase the specific energy at section 1, here we can see here this graph, this specific energy, let's say it was here E1, so E1 will move to the right. So from here we could not accommodate this delta z, but from this event we can accommodate the bigger delta z. So that's how. But as this energy increases, so the depth of flow upstream will also increase. And what will be the scenario at section 2? The section 2 will still be at the critical depth of flow, because this increase will be such that the delta z point will just touch the curve. This new E1 will be such that, so this point will still be at critical depth. So to summarize what all we saw, as we increase the height of hump, the depth at section 2 decreases, and as we keep on increasing, there will be a certain depth, delta z max will correspond to y2 is equal to critical depth. And if we want delta z to be greater than this delta z max, so for that upstream depth will increase and y2 will still be equal to yc. This is the case. Similarly, we can see for the supercritical flow also. So what will happen if the incoming flow is in supercritical zone? It is similar to this only, just the depth will be reversed. So this is the channel bed, and let's say this is the hump. So this was something, this is in the supercritical zone. So let's see from here first. This is the energy at section 1. Here is something section 1 and here it will be 2. So at section 1 energy is E1, and if we are putting the hump, so from here we can see that in the supercritical zone, as we put a hump, the depth of flow increases at section 2. From here we can see that this is the depth at section 1, and as we are putting a hump of height delta z, this depth is increasing. So from here this depth will increase, and as we move to the left, if we want to increase the height of the hump, this depth will further increase. This will come here. So here there will not be any change at section 1, but the depth will increase at section 2 as we increase the height of the hump. And so what is the maximum increase possible? It will come at the critical depth of flow. So this will increase to delta z max, and this height will be, this level will be yc. This y2 will reach yc. And what will happen if we further want to increase the height of the hump? That is not possible in this case, and the flow is called as choked. In the above condition also, when we have reached the maximum height of the hump and we further want to increase the height, so in that condition flow is called choked. So in choked condition, what happens? after this choke condition only this specific energy increases, and we can further pass the flow by increasing the upstream depth. So this is the choke condition, and what will happen after that? In this case, we want to pass the same discharge. So what will happen to pass the same discharge? This upstream depth will decrease. In the subcritical flow, what was happening? In subcritical flow, upstream depth was increasing to increase the specific energy. But as we are in the supercritical zone, the specific energy, to increase the specific energy, depth of flow will decrease. So to summarize, we can say that in the supercritical zone, as we increase the height of hump, depth at downstream increases, and it keeps on increasing until when we reach delta Z max, this y2 will be equal to yc. And if we further want to increase the height of the hump, what will happen? This y2 will still be equal to yc, but y1 will be less than what y1 was before, or we can say y1 dash, which is the increased height, which is the decreased height, it will be less than the height which was there before. And so if we want to find out the maximum height of hump, so how can we find out that? From the basic equation, as we saw, E1 is equal to E2 plus delta Z. So from here, we, for the maximum condition, this E2 will reach EC. So E1 is equal to EC plus delta Z, and EC, we, as we saw earlier, for rectangular channel, it is equal to 3 by 2 YC. And if you put it here, so delta Z max is equal to E1 minus 3 by 2 YC. This is how we find out the maximum height of hump, which is the maximum height without changing the upstream depth. And if the upstream depth is changing, then this upstream specific energy will also change, but the downstream depth will still remain at the critical depth. Now next is the width reduction. So this we can study from the unit discharge versus the depth diagram. So let's say unit discharge at this section is Q1, and at section 2 it is Q2, and we can see as the width is reducing here, so Q1 will be smaller than Q2. And from this diagram we can see that if I increase the depth, there are two cases. This zone here is supercritical, and this zone is here is subcritical. So what is happening here? One more thing here is the bed level is not changing. So just the width is changing, bed level is not changing. So what is the implication of that is specific energy will remain same at both these sections. Specific energy E1 and E2. So E1 is equal to E2 because there is no change in the bed level. So there are two cases, so subcritical zone and supercritical zone. So first let's see for subcritical zone. So what is happening? This unit discharge is increasing as we are going from section 1 to section 2. So here it is associated with, if the unit discharge here is Q1, this is Q1, and if I'm increasing this unit discharge to Q2, this is here is Q2. So it is associated with a decrease in depth. Here depth is y1, and here the depth is y2. Here we can show it like this is the depth y1, and as it is coming to the throat section, this depth is decreasing here. And so if we further reduce the width of this section, if we further reduce the width, this y2 will, this q2 will increase further. Let's say this q2 will come here, and so this depth will further decrease. So this depth will come down here. So how long can we do that? This is possible until we reach the critical depth. For that we have reached the q max, and for that this width will be b minimum. And here we can see that for if we want to further decrease the width of the channel, there is no possible flow. There is on this curve there is no possible chain. If we further want to increase q2, there is no intersection between the two, so no depth is possible between the curve and the line. So what will happen here, if I want to decrease the b after the b minimum, which is occurring at the critical depth, for that upstream specific energy will increase. So this curve is plotted for one specific energy. And now if I want to decrease the channel width further to pass that flow in this condition, this graph should change. So it will go something like this. This will be the new curve. In that condition only we can find out the intersection between this curve and the line for the increased discharge. Now in that case this E1 will increase, and what will happen to the section 2? As we saw, E1 is equal to E2. So E1 is increasing, then E2 will also increase. But corresponding to that, what happened here is, as we kept on decreasing the flow width, so this was decreasing, so minimum depth was yc corresponding to the energy E1, and here E1 here and E2 here. Both specific energies were same, but to pass the flow in after width reduction has reached b minimum, what will happen? This specific energy will increase, so correspondingly this specific energy will also increase, but this depth will be at critical depth, but it will not be the same as the old critical depth. There will be a new critical depth yc dash corresponding to the E2 dash, which is equal to E1 dash. This yc is corresponding to the E1, which is equal to E2. I think I have made it clear. Let me try to tell again. So in this graph we saw, as we are decreasing this width, what is happening? As we are decreasing this width, so this q2 is increasing, and if this q2 is increasing, so for that, to pass that q2, the depth is decreasing. So here we see that the depth is decreasing. So what is the maximum reduction in depth? The maximum reduction comes when depth has reached yc. So this E2 will be equal to EC, and which is equal to E1 also. But if we further decrease the depth, if we further decrease the width, which is not possible, in that case it is not possible to pass the flow, and then to pass the flow this energy will increase, and this energy will increase, so the energy at section 2 will also increase. but this depth of flow will still be at critical depth, but this critical depth is corresponding to new specific energy, and this critical depth is corresponding to the older specific energy. And similarly it will happen if the incoming flow is in supercritical condition. From the same graph we can see, from here we can see this is Q1, and if I increase it to Q2, as we reduce the width, this unit discharge will increase to Q2. So here it is associated with increase in the depth. So if the depth was here like this first for supercritical condition, so when the unit discharge is increasing because of the reduction in width, the flow depth will also increase. And if I further decrease the width of the channel, this unit width, its depth of flow will further increase at section 2, and the maximum depth of flow at section 2 will come when we have reached the B minimum, and this depth will be equal to YC. This is Y1 and here energy is E1. And if I further decrease the width, so that is not possible. So in that case what will happen? In that case the upstream specific energy will increase. To increase that upstream specific energy, the depth of flow will decrease. The depth of flow will decrease at the upstream, and the downstream depth will be equal to the critical depth, but again this critical depth and old critical depth are not equal. So to summarize that, I can say so first of all, as we are in the supercritical zone, the depth of flow increases. The depth of flow will increase as we reduce the B. As we keep on reducing, the Y2 will increase, and when B minimum has reached, the Y2 will be equal to YC, and till here there will be no change in the upstream flow conditions. And if I want to reduce the B less than B minimum, then there will be a new specific energy at section 1, let's call that E1 dash, and corresponding to that there will be new specific energy at section 2 also, which is E2 dash, and as we saw the specific energy is remaining same, and corresponding to this new specific energy there will be critical depth at section 2, which will be YC dash, and this YC dash will be greater than the older YC. And what will happen at section 1? If the flow is in supercritical zone and we are going below we are reducing the depth further B minimum, then if we are in supercritical zone, then Y1 will decrease, Y1 dash, let's say this is the new depth, this will be less than Y1, and if we are in the subcritical zone, then Y1 dash will be greater than Y1. That's it in this condition. And so there are some more points, important points in this case. This we saw earlier also, specific energy is minimum for a given discharge at critical depth. This also specific force as we defined is P plus M by gamma, and if we find out the dF by dy, and this is also, the result is also only important. This, from here also we can find out that q square T upon Ga cube is equal to 1. From here also we find out the same result. So which implies that specific force is minimum for a given discharge at critical depth, and discharge is maximum for given specific energy. This is the same line. The round number is unity. In the next video I'll solve some numericals, so it will be further cleared.